will continue our discussion on the conditional operator. So similar to other operators, let us define the truth value of P conditional Q. This is also known as implication operator. So you can also say P implies Q. What it says is the following. If this takes the value true, this takes the value true, then the truth value associated with the statement P implies Q is true. This is true, this is false, then the truth value associated with this is false. And this one is false and true, then this is true. This is false and this is false, this is true. So the expression is false when P is true and Q is false, and in all other cases it is true. P is also known as premise, Q is known as conclusion. So what is this telling us? When premise is true and conclusion is true, then the statement P implies Q is true. Premise is true and conclusion is false, then the truth value of the statement P implies Q, or if P then Q, is false. Interestingly, when premise is false, independent of whether Q is true or false, the truth value of the expression P implies Q is true. On one side, this is the definition. It defines the truth value for P implies Q depending upon the truth values of the proportional variables P and Q. Now, let us spend time and ponder on why, when conclusion is false, premise is true, we see that truth value is true. In all other cases, it is true. Consider this example. So, if I work hard, then I score grade yes. So we are interested in analyzing truth value of this statement given two propositions, I work hard and I score grade S. We look at possible values for P and Q. The definition says when it is true and false, it is false, rest of them it is true. Okay, let's analyze why. So we make a statement like this, and I work hard, then I score grade S. Both are true. When both are true, the statement says if I work hard, then I score grade S, which means the statement is respected. So this is the claim of the statement. If this is true and this is true, then the statement is respected, which means the truth value associated with the statement is true. I work hard and I scored yes. Then the statement is true, which is why P implies Q gets true when both are true. Let's look at the next one. Now P is true, but Q is false. The statement says I work hard if I work hard. If I work hard, then I score grade S. Then the statement is not respected. You have worked hard, premise is true, but you are not awarded grade S, you are not scoring grade S in that course, which means so and so claim is false. You can imagine like this. A professor is making a statement or a proposition: if I work hard, or if so and so works hard, then he or she scores grade S in so and so course. Now you have worked hard and you have scored S, then the professor's proposition or statement is true. And you have worked hard and you are not awarded S, so you are disappointed. So which means the claim or the statement or the proposition made by the professor is not respected, which means the truth value associated with the proposition is false. Which is why when it is true and conclusion is false, which means this has happened and this is not happening, then the truth value of the expression combining the action and the result is false. The next two are interesting. When should I look at this statement? It says if. If you work hard, only then this statement comes into picture. That is false now. For these two, premise is false. I am not working hard, or I didn't work hard. Whether you scored yes or you have not scored yes is independent. The statement is still true. Please note, this truth value associated with the statement is still true. Why? You can only invoke this statement when it is if. If you work hard. You don't work hard, then this statement is not in your picture at all. It is not for consideration. It is not for discussion. Then what is the truth value? The independent of our discussion statement is still true, because professor has made this statement that if you work hard, then you score grade S. So the truth value of this statement is true. You can only invoke and comment or change the truth value when premise is true and depending upon whether the conclusion is happening or not. When premise itself is not true, then we cannot take this into consideration for discussion. However, the truth value of the statement is still true. Okay, which is why when premise is true, the truth value associated with the conditional statement is true. Fine. Let me give you one more example. Okay. So, if I sing well, then I can compose songs at some time in future. Okay. This says when you sing well, you ask whether this is happening or not happening. You don't even sing well, or you are not trained to sing well, then this statement is not for consideration at all. Reason, there is a if here. If P, then you ask, is Q happening or not happening? If it happens, then it is true. If it does not happen, the truth value associated with the expression P implies Q is false. That's the interesting part of implication. On one side, you just accept the truth table as it is, but that is not something one should do at a master level course like this. One should ponder on and ask, introspect why it is false for this and for rest of them it is true. Experiment with examples like this and extract a larger message and work in the abstract world. That's something you should carefully switch between abstraction and real-time examples, and the observations, inferences, some learning that you get out of examples, you should immediately map it to the abstract world. Only then your mathematical maturity will start improving. And once your mathematical maturity improves and you are comfortable in the zone of abstraction, then when you start looking at the specific application, that could be from a data mining domain or biometrics, you can immediately model such a problem using something that you have studied before. And that's the purpose of study, right? When we learn something, we should apply somewhere else. And you should learn in such a way that when you see a new problem, you should be able to map it to something that is known to you. Okay? And the process of mapping is the real challenge. How quickly you can map, it depends on your mathematical maturity. The more you learn, the better you are in that subject, you get confidence and the mapping comes so nice, and you are always at ease for transforming a problem from one domain to another domain. Fine. So this is the interesting part of P implies Q. Now one can write this statement in many different ways. So I work hard only if Q, so I score grade S. So in English, this P implies Q mean many things. So scoring grade S is necessary for working hard. So Q follows from P. I score grade S follows from I work hard. Okay. So working hard is sufficient to score grade S. It makes sense, right? When you read newspapers, when you read articles, we get to see the usage of necessary, sufficient, and so on. Now it makes sense. Working hard is sufficient to score grade S. What is this telling you? You do this, you are rewarded with this. That is same as saying if P then Q. And scoring grade is necessary for this. So I worked hard. What is the reward I get? I get this. Okay. And when you work hard, it follows that you are awarded grade S. You may look at my scribe where you get to see more on these concepts, and the scribe is available at www.csc.iitdm.ac.in. So if you go to this website, there is something called teaching. Under that, lecture notes. Under that, there is a module on discrete mathematics. There you get to see a scribe on logic, more on this, examples, varieties, all that you can see over there. Our next operator is biconditional operator. If P and Q are true, then the truth value of this is false. When P and Q are true, the truth value of this one is true. When it is true and false, it is false. When it is false and true, it is false. when both are false, it is true. So it is true when both are happening and when both are not happening. If one is true, the other one is false, you get to see that the truth value associated with the expression P biconditional Q is this. So this statement also means this. P implies Q and Q implies P. P is necessary and sufficient for Q. P if and only if Q. They all mean one, which we shall verify now. Let's look at the first statement. So the first statement says P biconditional Q is equivalent to P implies Q and Q implies P. Let's verify. You have P and Q, taking the value true, 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 false, false, true, false, false. P implies Q says when this happens it is false, in rest of them it is true. Look at Q implies P, and true, false alone it is false, rest of them it is true. Correct? Now look at the AND operator. P implies Q and Q implies P. Both are true, so this one is true. Both are, one of them is false, so this one is false. One of them is false. Both are true. Now you see that the truth value of P implies Q and Q implies P is one and the same. Therefore, this one and this one are logically equivalent, which means in a logical context or an argument, if we find the expression P biconditional Q, you can always replace that with this. Equivalently, if you find this, you can always replace with this. Fine? Look at this one. When you say P is necessary and sufficient for Q, you can rewrite this as P is necessary for Q and P is sufficient for Q. Fine? So this one implies P is necessary for Q. So it implies that Q implies P. And P is sufficient, so which means it is P implies Q. So what is this? It is P implies Q and Q implies P. That's precisely what P implies Q and Q implies P. So saying this and this and this are one and the same. Look at the next one. P if and only if Q. This can be written as P if Q and P only if Q. What is P if Q? It is Q implies P. And what is P only if Q? Which is P implies Q. So this is precisely P implies Q and Q implies P, which is same as P biconditional this. So we may come across any of them when we look at an argument or in the natural language context, but in logic they all mean one P biconditional Q. And interestingly, P biconditional Q says you demand both P is necessary and sufficient, which is why you see that when both are true, logical value is true, and neither is true, then you don't even look at the statement. But the truth value associated with the statement is still true. But one of them is true whereas the other one is false, then you get to see that the statement is not respected, therefore the truth value associated with the statement is false. And it is a strict form of conditional operator where you demand not just P implies Q, you also demand Q implies P. More on this, some more example we shall explore now.